and welcome to today's video. Today we're going to be doing number 79, word search. So you're given an m times n grid of characters board and a string word, and you want to return true if the word exists in the grid. Okay. So we have an example here. We want to check to see if ABCCED exists, ABCCED, and it does because you can go in this pattern. Same thing with C, it can go in this pattern, and then same thing for ABC, B it doesn't exist, so you wouldn't want to do that. So, okay, this makes sense. Okay, well, just taking a look at this, my first initial thought is just to go through every single letter. So we have A, B, C, D, E, well, A, B, C, E. We take a look and then we look for all elements which have the word A in it. Let's go like here, A, right? And then what you do is you can do like a DFS on all of the ones which are adjacent. So we have A, B, S, F, we have B, S, F. B is here, so we go check this one, and then we keep going down the path until we arrive to the final letter. If we eventually reach it, then we have that as our final response. Otherwise, I don't see. Yeah, so we're gonna do that for every single letter, and if it doesn't match the letter, then you restart and you move on to the next character. So yeah, basically what I'm gonna do, loop through every single character, check to see, given a character, if it matches the first letter, we move on to the next iteration, so on and so forth. So the time complexity of this one, so for every single letter, it would be, you'd have to iterate through m times n initially, because you'd have to iterate through every single letter and figure it out. And worst case, you could iterate through everything over and over again. So it'd be m times n times the length of the words in the what you're trying to search for, because at the worst case, you could repeat that for every single one. I'll have to verify that later, but that's my initial thought right now. So I'll go ahead and begin coding this up. So we'll have, first of all, we want to loop through every single item in the board. So we'll do for I in range length of board, for j in range length of board. First thing is we want to iterate through and check to see if it matches the first word. So if we'll have like a current val, so we'll have that to equal to board of I and j, and if val is equal to the current word, we'll say what our current is. We'll have our current index. So cur index is going to represent basically how far we are along the word. So we'll have this at 0, and if it eventually reaches the end, which is basically the length of the word, then we'll return that as our final answer. So we'll return true. If the val is equal to word at the current index, then what we want to do first is we want to return. We want to keep going forward, so that's good. And then we want to move on, and then this is where we're going to do our DFS. So we want to do a DFS. Yeah, we want to do a DFS on the actual word. We want to do a DFS on the next iteration. So we can actually turn this into a function. Yeah, we can turn this into a function actually. So actually, yeah, we'll do like a def DFS, and then given this DFS, we're going to be given, let's say we have an I and a j here. So we want to say where we are currently. We want to see what the adjacents are. Okay. Okay, wait. So actually, so we'll have this, and then we'll do our DFS like we were talking about earlier. So def DFS, as parameters, we can take in adjacents to like basically pass in the adjacent letters around what our current one is, and then we'll actually have to pass in where we are currently in our index. So this adjacent will be a list of the letters which are adjacent to it, and then we will also simultaneously add the current index to it. Yeah, our current index plus 1. Yeah. Actually, we'll start off with 1 here. We actually don't need to have this current index, because what I'm thinking of is I want to add the 1 start off here because we move it forward, and then we can have current index as a parameter, and once this reaches it in DFS, that's when we can return true at the very end. So we'll do a DFS with our lettering, and then we'll also have maybe another helper function which returns a list of all of the adjacent letterings if they exist. So return adjacent, and then we'll have this, and we'll be given an I and a j. If so, list. Actually, we'll have an adjacent here and have it equal to an empty list, and then if the adjacents, yeah. So if board I plus 1 j, actually, yeah. So if I is less than the length of the board, yeah, I plus 1 is less than the length of the board, and j, yeah. So we'll have this. We're gonna want to adjacent dot. We're gonna want to append this. Board I plus 1, and then j, and then we're gonna want to repeat this for every other sequence. So same thing. Less than 0. Oh wait, yeah. So if I plus 1, this will just append it like this, and then if this is less than 0, or sorry, greater than 0, then we want to append it as well. And then same thing, keep on going. The reason why I'm having 0 is because we want to grab the first element, because that's what j is going to be. J is going to be like yeah, like how far you're going down. And then okay, so we'll do this. G minus 1. Wait, oops. I'll have to make this I, and then j minus 1 over here. Okay, so at the very end, we can return the adjacents. So we have this. Yeah, 5 plus 1, we want to append, basically grab all the adjacents, if they're not out of the area. Yeah, and then we'll add that in. Yeah, so we're gonna want to add, yeah, basically add, this will grab all the adjacents. To be honest, all the adjacents we need to grab is just any one that's in the next all the adjacent that we need to grab is the one that is the next available in the word. So we'll have, maybe what we can do is we can have a needed variable, the needed variable, let's say like we're at ABCCED, we're at A, our next needed is going to be B. So what we can do is we can pass it in as a parameter here and grab that, and then we're gonna want to return the index of the next one. So instead of the list, it's going to be searching it for us. Yeah. Okay. So yeah, kind of pivoting away from my original idea, but I want to see how this goes. So yeah, we're gonna have a needed, and then we want to check to see, and okay, and board I is equal to needed. If this is equal to needed, then we will want to return the index of the next one. So let's return this. And same thing. We want to return this one. Or actually, we don't want to return the value itself. We want to return a list containing the actual coordinates itself, because that's what we want to move forward with for our next one. So we'll do we have j minus 1. Same thing again. Oh, sorry, this is j plus 1. This other one's j minus 1. Quickly modify this. Oh, sorry. Then we go with this one. Oh, right. And then we want to return I and then return j minus 1. Okay. Another thing we actually need to do. Okay, yeah. I don't think, yeah. Diagonals. Yeah, it has to be horizontally or vertically neighboring. So I was thinking for a second, oh, we need diagonal numbers, but it turns out, yeah, we actually don't need it. So we have this now, where we have our values, and then we can return them. What we want to do next is we want to check to see, we want to turn the adjacents if it exists. So this is what we call our DFS. Yeah, so we'll do a DFS on our current, instead of having our adjacents, we have a DFS starting with our current, or coordinates I, j, and then we have our current index. So what I can think of doing now is we do a DFS given the I to j. Actually, we'll just make this a little bit simpler. If the value is equal to the word at the current index, you want to do a DFS on I and j. And then for our current index, we're going to start off with 1. And then for here, what we want to do is we want to check to see if return, So if return adjacent I, j, and our needed one. So our needed one is going to be the word at the word at the current index. So if the board value is equal to the number, what we're going to want to do is this is going to return the coordinates of the next available one. So we want to actually, so if return adjacent, we'll have this next step. We can have that set to this method here where we return the next adjacent, and then this should grab something similar to, let's say, like it'll be like we'll start off with A, it'll grab like this will be 1 and then 0, because this is going to be our next available one. And then if this exists, it can be either 1 or 0, or it can be false if no other adjacents which match what's needed is. So if the adjacent exists, then what we can do is if the adjacent exists, what we want to do is return we want to keep on moving to the next one. So if next step, then we want to do a DFS on, okay, so I actually, instead of this, we can do I and then J, and then if I and then J actually, let's just keep it next step for now. So we'll have next step, and then we'll have if this next step exists, then we can turn I and J equals next step. We can separate it out into different variables. Oh, this is a DFS here. I next, and then we'll have J next. If the I next exists and the J next exists, if next step exists, then we're going to want to separate it out into its own indices and then call it on the next step. So I next and then J next, and then we'll want to have the current index up by 1, index plus 1. And then if you manage to make it to the very, very end here, what we can do is return, we'll have like a if statement. If cur index is equal to the length of the word minus 1, then we want to return true, else we want to keep doing this one, and then at the very end we'll want to return false if we never return true at the very end here. So keep on moving forward, and then at the very end we'll want to return false. Okay, so just to check if we're missing anything, I'll run this through. We start off at A. We start off at A, and then we check to see basically, is the word equal to the current index, which is, we don't have a current index right now, so we'll want to see if it's just equal to the first letter in the sequence just to kick it off. Well, let's say like A does, so we move on to have the index be 0, 0, and then 1, because that's going to be your first index. So now we check to see, is it equal? No, it's only equal to 1. And then you call return adjacents, which will then return all of the adjacent ones. It'll grab all of it, right? So it'll grab B, S, F. It'll return, it'll check to see if any of those are what's needed. And we know what's needed by grabbing word 1, right? Because we pass in 1 as a parameter here. We check to see, are any of them equal to B? Turns out 1 is. So then we return that as our, basically, as an array. And then we check to see, does it exist? Yes, it does. So then we move on, and then we go ahead and do next. We check and see what the next step is, basically by separating it out, and call DFS again, adding onto the current index by 1, and eventually it'll return true. If it manages to do a DFS on everything and there isn't anywhere where it does so, it'll go ahead and return false at the very end here. So I'll go ahead and run this probably some mistakes here and there. Okay, let's see. A, B, C, D. Oh wait, this is exactly our board. Okay. In order to debug this, why don't we go ahead and print out we'll print out the current word that we're on. So we'll do I, J, and then word I, J. I just want to see what's happening to the DFS call as we do so. Oh, wait, we just want to return true. Seems like the index is out of range. Oh, sorry. It's got to do board. So we start off at 0. We go A, B, C, C, E. Oh, but we're missing the D. And why is that? Let's check. It's checking the left, so that would be the I one. So it's something wrong with the I minus 1. I minus 1 is greater than 0. 0, 1, 2, and 1, 2. E. It's not grabbing the final one. And why is that? A, B, C, E, E. Oh, maybe it has to equal the length of the word. A, B, C, C. A, B, C, C, E, D. Yeah. A, B, C, C, E, and then D. Oh. We need to return the next value here as we do this. Because it's the nature of the DFS, yeah. Okay. So this one seems to work. Second one, C. It's grabbing 0. Oh, sorry, 1, and then a 0. Oh, and then it's just stopping. Oh, we only want this to happen if it actually, if divest this one, then return true. Otherwise, we want it to keep going. Yeah, so. If at any point this is equal to true, you want to return true. Otherwise, we want to return false. Now, why is this returning false? It's going 1, 0, S. So it's grabbing the first one, it's checking to see, and the return distance is going to be false. And then you return next step. Oh. I wonder if we need to make it explicit as we do so. Okay. Nope. Never mind. Okay, let's see. It's going SCC, and then it's not returning true, obviously, it's returning false. But why is that? Return DFS if the next step exists. Let's just print out what next step is. Well, next step never exists because it's returned to false. That's supposed to happen. So then it just ends there, and then it should move on to the next one. It doesn't seem to be catching the final one. Oh! Silly me. Okay, yeah, forgot to grab it by the actual amount of columns and like versus opposed to rows. That's why I was ending a little bit early for the second one. Okay, final case. It's returning true, but it's expected false. We go A, B, C, B. Oh, you can't go back to its original one. That's an edge case that I need to remember. An edge case, yep, need to remember that. In order to prevent that, I think that's relatively simple. We just need to know what our previous was. So we can have a previous accumulator here, and then as we return adjacents, our previous can be I and then J here, and then we'll have to make sure that that this is not here. So if I plus 1, I prev J prev equals prev. If I prev, if I previous is not, if not, I prev equal to I plus 1, if not, I prev J prev equal to I plus 1 J. We'll have to add this for everything. I prev J prev I minus 1 J plus 1 J minus 1. Return false. Go ahead and run this. A, B, C, B. It's still going. If not I prev and J prev is equal to I plus 1, and then J, I minus 1, and then J, I, and then J plus 1, and I, J minus 1. Yeah, if it's not equal to each other, right? We need to pass in the previous as I and J. Wait a minute. I'm just passing an I and J over again. This doesn't make sense. Oh, okay. I see. So we need to keep track of what the previous is. So we'll have to have a previous here. We pass in I and then J. Yeah, that's what we do. We pass in the I and the J, and then we pass in the previous here. Yeah. Okay, because we need to do the previous step. Oh, right. Call on this, and then we have. Oh, if we start off at the very beginning. Well, this won't be happening, so it'll just be like. Oh, doesn't really matter either way. We can call it whatever because it's not going to affect it. Let's just say it's I and J. Nice. Fully accepted. Go ahead and submit this. See if there's any other issues. Okay. Let's see. 56 out of 87. A and B. B, A. 01B. But it's not grabbing A. Looks like it's a indexing issue. We have A and B. B and A. Let's use this as a test case. We start off with the word letter B, and then it doesn't go forward anymore because it can't find any adjacents. Well, let's print out the next step. It doesn't even call the next step because there's no more adjacents. Let's see. It shouldn't affect it, though, but let's see. Yeah, it's out of range. So it is grabbing the last possible one. But there's no adjacents when it grabs it. You have your A, your I, and your A, and your B. Start off here. Call that I and J. We call it I and J. Maybe it does matter. Because I and J is your previous. Well, it shouldn't ever grab your previous. It returns adjacents with I and J, and then it gets your needed, and you also have your previous. And it can't be I and J, it can't be the one previous before. But when you call this, it's not equal to the needed. Let's just print out all the values. So we print out I, J, needed, prev. We run this. Okay, so we have 0, 1 are needed. 1 is an A, and then our previous is 0. Yeah, and then 1. That's a previous, yeah. And then it's not grabbing the other ones then, huh? For one specifically, we have A and B, and that's going to be our left. So our left is going to be J minus 1. Oh! Wait, no. I and J minus 1. Oh, that might be it actually. Oh, right. Needs to be greater or equal to 0. Okay. Getting closer. AAB. Oh, it's going doubles. We need to have a previous set. It needs to be a set of the indexes in which we've already used up, not just the previous value, because you'll have situations like this where it'll keep bouncing back and forth. So we'll have a set. Instead of this, we can have an empty set, and then we'll check to see, instead of here, if not in set, so if it's in prev, if it's on the previous and this is equal to that, then we'll keep on going, and then we're going to want to add that to our next available. So we want to return that, and then we eventually want to do turn DFS, and then we'll do prev.add prev.add our copy. So we'll do copy and then I and then j. That should be good. Use test case, run this again. Erase that, and then we'll call. Oh. Okay. Go I plus 1, j, I minus 1, j, j plus 1, oh sorry, I, j plus 1, then I, j minus 1. Run this again. Unhashable type list, okay. Oh. Shoot, okay. Okay, well, to make it hashable, we can turn it into a tuple. Yeah. Tuple, and then same thing for the other ones. Go ahead and add the tuple value of it, and then we'll go ahead and submit again. We add the sets, and then we'll do prev.add. Huh? Argument of none type is. Let me just search up the syntax. Is that? Oh. Yeah, actually, why don't we go ahead and do this instead? So, I think I just have the syntax wrong. Then we'll have that. Check, make sure. I and j is not improve. Let's take a look at the error actually. If in And we're not passing this in as a parameter. We I current index, and then I current index, and then return I index, and then prev dot add. Okay, so we have A, and then B. Okay, let's print out, along with this, we'll print out the prev. Oh, okay, we'll do this. We'll do prev. I'll do prev dot remove I and then J. Oh, there we go. Yeah, because we want to add this, have it as a previous, and then we remove it as we go to our next possible step. Yeah. Okay. So we're adding 0, 1, and then we're adding 0, 2. Or do we need to remove this at all? Let's try this. Okay, actually we might need to remove it. We have a set 0, 1, 0, 2. Oh, okay, this needs to be outside of the DFS. It's only having one item in the set at a time. So we'll do if sets, it adds it. Prev. We add a new prev copy equals prev dot copy, and then we do prev copy dot add I and J, and then prev copy dot remove. Go ahead and run this. Oh shoot, same thing. It's constantly doing that. Why is it only removing it? Let's see. Okay, actually, I think we're repeating this too much. So what we can do instead is maybe just convert this, or not convert it, but put it all into the same DFS method. So instead of having a next step and then all of this, we can do basically a look where we check to see for I and then J in I plus 1, and then we do the same thing over again, and then J, we'll have a tuple of this. I minus 1, J, I, J plus 1, I, J minus 1. We'll loop through everything, and then we'll do the DFS. So we'll do if it's between 0 and then I, and then we need to change the variables for this one actually. We get x and y. If x is less than or equal to 0, which is less than the length of the board, 0 is less than or equal to y, which is less than the board 0, and x, y not in previous. Yeah. And board x, y is equal to, the board is equal to the current index of the word itself, what's needed in this case. Yeah. then we want to add it. So we do prev.add, and then we do x, y, and then we do if the DFS of the x, the y, the current index plus 1, and the previous, then we want to return true. Otherwise, we just want to remove x and y, and then return false if this doesn't happen. And then this negates the need for this specific method. And then let's run this again. Oh. We do a quick run through. Not supported between instances of ints and a list. Oh. What am I? Gotta change the length. Oh. Less than. Oh, okay, finally. Accepted all test cases. Yeah, just switch the X around. Oh, okay, let's see. We have AAA. Ooh. Oh, actually, we need some. Surrounded by brackets. So once we remove the print statements, then we'll run this again. Oh. Okay, nice. Finally, we submitted our test cases, and everything's working good. Time complexity is going to be O of O of m times n initially, and then for every single one, we're going to be trying every single possible combination. So it should be O of m times n times... yeah, like I said earlier, O of m times n times the number of possible like words there can be. So m times n times the number of possible word combinations. So m times n times w, let's say. I'm actually not too sure about this. Oh, okay. O of 4 to the power of n. Oh, I see, okay. So it's O of 4 to the power of n, because you can go in 4 different directions. So 4 possible different directions, and then you go for every single one. You can do that with basically n combination of basically n represents the number of elements in the array, and you can do it 4 times, 4 to the power of the number of elements which are in the array itself.